Hello there, Mr. Sutton here, bringing you the AB Calculus 5-9 Extra Practice Number 3 solutions on FTC Graphical Analysis. For this problem, we're given the graph of f, and we want to know the integral from -2 to 3 of this graph. So basically, we're just finding the area under the curve of f between -2 and +3. We just have to keep in mind that area that is underneath the x-axis is going to count negative towards this. So going from left to right, the first shape I see from -2 to 1 is this trapezoid. So this is going to be, let's see, a base of 3 plus a base of 2 over 2 times a height of 1. So that's going to be our first area. And then from 1 to 3, we're going to have this triangle area, but this is going to count negative because it's underneath the x-axis. So this is going to be minus 1/2 times a base of 2 times a height of 2. And then just simplifying this because we have to match one of the answer choices. This one is going to be 5 over 2. And we're going to be subtracting, let's see, this is just going to be 2. So this is 5/2 minus 4/2, which is 1/2, giving us answer choice A. On this problem, I've got the graph of f here, and h is defined as the integral from 0 to x of the f function. We want to know where h has an absolute max, at what x value. So for absolute max, we have to consider both the endpoints and critical values. So for critical values, we need to figure out h prime. Now, since h equals this integral that has an x in the upper limit of integration, we can just use our fundamental theorem to find h prime and take the derivative of that integral. Basically just going to substitute the x for the t in the dummy variable here. So this is going to be h prime equals f of x, which means if you want to find critical values for h, you just need to figure out where the f function equals 0. Now we're going to do a little bit better than that because not all critical values are created equal. If we're looking for an absolute max, specifically, we're looking for places where f is changing from positive to negative. We're looking for local maxes. Local mins we don't care about. Critical values that are not local mins or maxes we don't care about. Just local maxes. So we see that f is changing from positive to negative at only x equals 0. There's another critical value at -2, but it's going to be a local min, so we don't need to really worry about that when we're finding the absolute max. So we need to test out x equals 0. We also need to test out -4 and +3, the other two endpoints. So let's go ahead and do h of -4. So that's the integral from 0 to -4 of f of t dt. Now we have to be careful here. Since you're going from a higher to a lower number, you're basically integrating backwards. So whatever area you would have gotten is going to be the reverse of the signs anyway. So we've got a few shapes if we go from -4 to 0. We've got this triangle and this other triangle. But now this first triangle, this would have been negative area since it's under the x-axis. But since you're integrating backwards, this now becomes positive area. So we're going to have 1/2 times a base of 2 times a height of 2. And for this other triangle, this would have been positive area, but you're integrating backwards, so this now is negative area. So we have 1/2 times a base of 2 times a height of 1. And adding that up, let's see here, this is going to be just 2 minus 1, which is just 1. Now we have to figure out h of 0, h of the critical value. So for this, we're just doing integral from 0 to 0 of f of t dt. And we don't really need to think too long about this one. If you have the same limits of integration, then that's just an empty integral and you have an area of 0. Finally, we have h of 3, integral from 0 to 3. So for this one, we could start finding triangle areas, and there's a trapezoid in here as well. However, since all of this is underneath the x-axis and you're going from left to right, we know for certain that this is going to be a negative number. Since we already have numbers that are not negative, we know this is not going to be the absolute max. So out of all these possibilities, we have a 1, we have a 0, we have a negative. 1 is going to be the absolute max, and that happens at x equals -4. So that's going to be choice A. On this one, g is the function defined as the integral from 0 to x of, well, all this craziness. And this is on the interval from 0 to 3. we want to know at what x value on this interval g attains a relative max. So what we're essentially asking here is, where does g prime change from positive to negative? To answer that, we first need to know what g prime looks like. Since g is this function with this variable in the upper limit of integration, to take the derivative of this and get g prime, all we have to do is use our fundamental theorem and basically plug the upper limit here in for the dummy variable. So we end up with negative 3/4 plus x plus cosine of pi over 4 x squared plus x, all this, and now we just need to see where this craziness changes from positive to negative. Now this is a graphing calculator question, so let's go and check it out. So here I am on my grapher. I've entered this g prime function as my y1, and I'm going to graph it now. I'm going to go to window first though, and I want to do this from 0 to 3 because that's the interval they said that this function is actually valid in. So 0 to 3, whoops, go back there, 0 to 3, there we go. And let me do zoom fit. Now I'm going to zoom 0. So here's our g prime. We're looking for positive to negative, and we've got one spot right there. Here's a negative to a positive, and those are really our only two critical values. Again, we want positive to negative. So let's figure out what this intercept is. So to find that, I'm going to go to second trace, option 2, 0. And let me go a little bit to the left of that intersection. There's my spider. And let's go a little bit to the right. Press enter again. Press enter a third time now. And we end up with about 1.025 if we round it off. So there was my graph. There was my x value. Since g prime changes positive to negative at this x value, that means that g attains its relative max at that value. So we end up with choice A. For this problem, we're given the graph of f and also a whole bunch of locations of horizontal tangent lines, which is basically telling us where the graph is turning around. G is defined as the integral from 0 to x of f of t. We want to know where g, the graph of g, is both decreasing and concave up. So in order to figure out what the graph of g is doing, it would be helpful to know what g prime is doing. So g prime, that's going to be the derivative of all of this. Since you're taking the derivative of an integral that has an x in the upper limit of integration, we can use the fundamental theorem of calculus and basically just plug x into the dummy variable t here. So we can write g prime of x just equals f of x. And now if we want to know where g is decreasing, we basically are asking where is g prime negative. If we want to know where g is concave up, we're asking where is g prime increasing. And since all of these things really are just also talking about the f function, which is graphed up here, we're asking where f of x is negative and increasing. Well, looking at our graph, we're negative from -2 to -1, but we're only increasing from, this is going to be negative 1.7. That's why they gave us this horizontal tangent line location. Negative 1.7 to -1. And we're also negative and increasing right here in this little stretch from positive 1.7 to 2. Since we're negative and increasing for g prime on those intervals, that means that g again is going to be decreasing and concave up on those same intervals. Looking at our answer choices, we only have one interval listed for each of these answer choices, so we're just going to pick whichever one has at least one of these intervals. So let's see here, -1 to -0.7, nope. -0.7 to 0, no. 1 to 1.7, not so much. 1.7 to 2, that's one of our two intervals, so choice D. On this problem, we are given the graph of g, and we're told that the f function is just the integral from 4 to x of the g function. We want to know the value then of f of 8. So just plugging 8 into this function here, we're just taking the integral from 4 to 8 of the g function, which basically means finding the area under the curve of g from 4 to 8. Since we're moving from left to right and we're above the x-axis, this is all going to be positive area. To find this area, we actually have to split this up into two shapes. Let's see here. We've got, what two shapes do we have from 4 to 8? We have a triangle from 4 to 6. We have a trapezoid from 6 to 8. So from 4 to 6, this is going to be 1/2 times the base of 2 times a height of 4. And then from 6 to 8, we have a trapezoid with bases, let's see, 4 and 2. So we have 4 plus 2 over 2 times a height of 2. Okay, let's simplify this a little bit. So half of 2 is going to cancel. We just have 4 for that first term. Second term, those 2's are canceling, so you've got 6. 4 plus 6 then gives us an area of 10. So that's choice C. For this free response problem, we're given this function f continuous on the interval from 0 to 4, but note that 4 is not included in that interval of continuity, so we might be discontinuous at 4. We don't really know. The function is twice differentiable except at 2, x equals 2, and the function and its derivative have all the properties in this table, and they even put DNE on there for does not exist. Okay, so for 0 to 4, this is our first task. From 0 to 4, we want to know all values where we have a relative extreme for f. So that could be either a relative min or a relative max, and then determine whether it is a min or a max at these values. So we're basically looking for where f prime then is changing sign. So taking a look at the table here, we've got these different values, and then we have the intervals between those different x values. So we see that f prime is changing sign only at x equals 2. We're changing positive to negative there. There's no other sign changes that they're telling us about. So because we're changing from positive to negative at x equals 2, because f prime is changing there, and we know that f actually exists there, so it's not, this DNE isn't coming from f not existing. Since f prime changes positive to negative at x equals 2, that tells us that f has a relative max at x equals 2. And that's it. For this problem, on the axes here, we want to sketch a function that has all the characteristics that they gave us of f. Well, let's start with the actual location that f is at. So we know at 0, f of x is at the location -1, so let's put a point down there. And then we have the point 1, 0, and then we have 2, 2, which is going to be up here. Then we have 3, 0, so we're back to the x-axis. And 4, well, we don't really know. So we're just going to have to wait and see on that. Now let's take a look at these different intervals. We've got, let's see, 1, 2, 3, and this is a 4th interval, even though we don't know where we're ending up. So let's take a look at whether we are increasing or decreasing on these intervals. And I mean, some of these are pretty obvious, but let's just look at the derivatives just to be sure. So from 0 to 1, we have a positive f prime, so we're increasing there. And from 1 to 2, positive f prime, so increasing there. And this matches with what these points are doing. And then from, let's see, 2 to 3, negative f prime tells us we're decreasing. And this is the next one that's going to be even more important, because we don't have a point for x equals 4. They said f prime is negative between 3 and 4, so we are decreasing again after we get to x equals 3. Now the last piece is the concavity, which is what this f double prime is telling us. Since f double prime is negative from 0 to 1, we're going to be concave down. And then from 1 to 2, positive f double prime tells us we're concave up. And then from 2 to 3, we're concave down again, negative f double prime. And then finally concave up for 3 to 4 because we have an f double prime that's greater than 0. So we just have to draw each of these branches now. So from 0 to 1, we need to draw increasing in a concave down fashion. So we're doing like the left side of a downward parabola there. And then we have to do increasing concave up to get from 0 to 1, or rather from 1 to 2, x equals 1 to x equals 2. So we're doing this kind of thing. It's like the right side of a parabola. And then to go back down, we're doing concave down sort of motion. So like the right side of a downwards parabola. And then we're concave up again, decreasing, so like the left side of an upwards opening parabola. And there's a graph that has all the features that they gave us in the table. For this part of the problem, we're defining a new function g as the integral from 1 to x of f of t. And we want to find all x values where g has a relative extreme, and whether it's a max or a min, with justification. So if I want to know if g has a relative extreme, I need to talk about g prime changing sign somewhere. And g prime, if you use your fundamental theorem here, you're basically just going to be plugging this x into the dummy variable in the integral here. So g prime by the FTC, g prime is just f of x. So if we recognize this, now we're really just asking where is f changing sign. So we see that f is changing sign in our table here from negative to positive at x equals 1. Since I changed negative to positive at x equals 1, and this is really g prime we're talking about, that means that g has a relative minimum at x equals 1. Now, f is also changing sign from positive to negative at x equals 3. Since f, also known as g prime, is changing positive to negative there, that means that g has a relative max at x equals 3. For this last problem part, for the function g from part C, we want to find all x values where g has a point of inflection. So recall from part C that g prime was really just f of x, because g was essentially the integral of f with an x in the upper limit of integration. So that means that g double prime, which is going to tell us about points of inflection, is really the same as f prime of x. Well, f prime of x is changing sign where in the graph? Only one place, actually, at x equals 2. So since f prime is changing sign at x equals 2, specifically from positive to negative, this tells us that g double prime is changing sign there, which tells us that g has a point of inflection at x equals 2. And just as a quick sanity check here, remember, a point of inflection, we're supposing that the original function actually exists there, and we see that f exists there, which means that g, for which f is the derivative, must also exist. If we're differentiable, then that means that we are also continuous there. So we're good. For this problem, we are given the graph of f prime, and we're told we have horizontal tangent lines at 1 and 3, and function is twice differentiable, f of 2 is 6, good times. Okay, so first thing we want to do is figure out where f prime is changing direction, or at least reversing direction, because if you want a point of inflection, that's talking about where f double prime changes sign. So we're talking about then where f prime is changing from increasing to decreasing, or from decreasing to increasing. We see that f prime, which is graphed here, changes from increasing to decreasing at x equals 1, and from decreasing to increasing at x equals 3. So at 1 and 3 we have these direction reversals, which proves that f has points of inflection at both of those x values. For this part, we want to know at what x value the f function gets an absolute min and an absolute max. So let's tackle the absolute min first. We see here that f prime is less than or equal to 0, but at least not positive on the interval from -1 to 4, and it's going to be greater than 0 from 4 to 5. So basically that means f is decreasing until you get to x equals 4, and then it's increasing after that. Essentially, we have a local min at x equals 4, and it's the only local min. So that proves that we're going to have an absolute min at x equals 4. Because if you're decreasing until you get there, nothing before 4 is going to be a minimum, and if you're increasing after that, it's not going to get any better, or at least any more minimal after 4. All right, so let's talk about the absolute max now. We can't use this kind of reasoning, unfortunately, for the absolute max because there's no local maxes here. There's nowhere where f is changing from positive to negative. So there's nowhere where we can say that f is changing from increasing to decreasing. But that in itself gives us a little bit of a clue here. Since f prime does not change from positive to negative anywhere on here, since there's no local maxes, that means that the only place the absolute max could actually occur is going to be at the endpoints, either at x equals -1 or x equals 5. So taking a look here at both of these, we would calculate these by taking some initial value and adding the area under the curve to that value as you move from left to right. You'd be acquiring area. But take a look at all this area under the curve. To get from -1 to 5, to figure out basically what f of 5 is, we would have to do some number plus the integral from, let's see, -1 to 5 of f prime. But that integral is clearly negative. We have a whole bunch of negative area here, and there's only a little bit of positive area here. Certainly, nobody is going to claim this is enough positive area to offset all the negativity that you acquired up to that point. So in going from -1 to 5, you're actually losing value for your f function. So what that tells us is that f of 5 is going to end up being a smaller number than f of -1. which tells us that our absolute max, since it can't occur in between here because there's no local maxes and it's got to occur at an endpoint, our absolute max is going to have to be at x equals -1 because you only lost area as you traveled from -1 to +5 with all this negative area under f prime. On this last part of the problem, g is defined as x times f of x. We want an equation for the line tangent to the graph of g at x equals 2. Well, to get a tangent line, we need an x value, a y value, and a slope, and then we can just plug it into point slope. We've got the x value. To get the y value, we just need to plug 2 into the g function here. So we've got a g of 2, which is going to be 2 times f of 2. Well, what's f of 2? F of 2 they actually gave you in the problem right here. They said it was 6. Nice. So this is just 2 times 6, which is 12. So we've got our y value. Now we just need the slope. We need to find g prime of x. For that, I'm going to use the product rule. So u prime v plus uv prime. Let me set up my box and ribbon over here. I've got my u value, which is going to be x. V is going to be f of x, the thing that x is being multiplied by. And the derivatives, u prime and v prime, it's going to be the derivative of x, which is 1, and derivative of f, which is f prime. Now, I just need to plug 2 into this derivative to figure out g prime of 2. Let me do that inside the box, though. So if x equals 2, what does each of these different components that we're going to put together out here actually equal? Well, if x is 2, then x is 2. Well, that was easy. If x is 2, f of 2, well, we already saw that right here. F of 2 is 6, so we kind of got that one for free as well. 1 is just a constant. It doesn't matter what x is. And then f prime of 2. Well, what's f prime of 2? Here's a graph of f prime. We can just look it up on the graph. At the x value 2, f prime has a value of -1 because we have the point 2 comma -1. So that value is -1 right there. I'm using the ribbon to put it back together then. G prime of 2 is going to be 1 times 6 plus 2 times -1, or minus 2 times 1, either way, same thing. So basically 6 minus 2, which is 4. Putting all of this into point slope, we've got y minus the y value 12 equals the slope we just found of 4 times x minus the x value they gave us of 2. There's your tangent line.